Thank you, Sohail. Yeah, so I'll be talking about a couple of the things that I've been working on this past year. And, obviously, a lot goes into it. It's a total team effort. Everyone except Tariq and Pat are here. You probably, heard from Veselin, Zanio, Vladimir, Boyan, and Matthias are in the back over there. So I'll start off with talking about bounding high-order functions and then talk about some recent developments in high-order mesh optimization. The motivation for the first work is, computing extrema of high-order functions is non-trivial, right? So if you look at the function over here, it's a cubic function. Let's say you're interested in finding the minima. You can see there's about 3 local minimas, 2 of which are quite close to each other. So you're going to solve an optimization problem. It's going to get expensive to ensure that you have figured out the global minima. And this comes up in various applications. One of them is ensuring mesh validity, right? So if you have a high order element, we all know that means that the position function might be a high order polynomial from reference space to physical space. But in terms of mesh validity, when we talk about the determinant of the Jacobian of this mapping, turns out that is also a polynomial. So ensuring mesh validity translates to computing the global minima of this function in each element and checking if it's positive or not, right? So in this case, it's a second order element. The determinant of the Jacobian ends up being a cubic function. And as I said, solving an optimization problem, going to be very expensive, not feasible. So one of the ways is you just sample at a lot of quadrature points, right? That's one way it's been traditionally done. And it becomes expensive and it's not robust, right? You can use a set of quadrature points and you might catch that negative determinant value, and you could increase the quadrature rule and then miss it again. So it's not robust. Another popular technique in the literature is using a positive basis. So people use Bernstein bases, and then as long as your coefficients are positive, you can ensure or you can guarantee that the minimum is going to be positive, right? But as you see in that chart over there, right? In this case, I know the minima is 2 times 10 to the negative 4, but starting with my element, the minimum coefficient is negative 0.4, right? So I'm like ways away from the actual minima. And then I could refine my element to get a better approximation, and you see, how slowly it's converging towards the exact minima. So, Bernstein works, but we want to do better. So, spoiler, what we do is we build a piecewise linear envelope around your higher order function. And the key points are highlighted over there. This method is relatively cheap, it's robust, and it comes with this user tunable compactness knob. Okay. And I kind of show what the end results look like with this envelope, and then you can sample your envelope to figure out. Yeah, as it turns out, it's much easier to figure out what the bounds are with this envelope, right? And shout out to James Lortis. This method it's kind of based upon what he did in GSLib for bounding nodal position function to compute bounding boxes, and in this work we've kind of extended it and generalized it for bounding high order functions with different bases, and yeah, doing different tricks to increase its effectiveness. Okay, so let's get into the problem. We have a high order function, and as we all know, usually in FEM, our solution is represented as a weighted sum of some basis function, right? In this case, I'm showing fourth order bases. These are Lagrange interpolants on Gauss-Lobato points. That's what you see on the left. And then on the right, I show what the function ends up being with those nodal coefficients. As I said, we want to find some bounds or some, the minima or the maxima of this function. All right. So how do we do it? As I pointed out, we're building a piecewise linear envelope around the function. So that kind of hints at our approach. What we're going to do is we're going to first compute piecewise linear bounds of our bases. Okay, so for each basis phi I, we're going to build a lower and an upper bound. And to define these bounds, we're going to first choose a set of control points that you see. These, you could choose your nodes, but you might want flexibility on what's your like x coordinates for this envelope. So these are represented by eta in the chart over here. It doesn't need to be the same as your nodes. And then you pick your value so that your function is enveloped. Okay. I'm going to talk about how we do it later. But let's say you have the bounds for each basis. So this is the first basis, second basis, third basis, fourth basis, and the fifth basis. Okay. So I have the bounds for each of the bases. And since my solution or my function is just a weighted sum of the bases, the upper bound would be, take the maximum for each function, the upper and lower bound of individual bases, right? Why are we doing that? Because, your coefficients might not be positive, right? So if your coefficient is negative, you probably want to use the lower bound for the bases. And you can do the same thing for the lower bound on the function. And we'll see how, this just doing this summation results in giving you the bounds. So I'm going to do a cumulative sum in this like bottom graphic. So over here, I just show the first basis function with its bounds scaled by the first coefficient, add the second basis and the bounds to it, third basis, fourth, and fifth. So you see how we have recovered the original function and an envelope around it. And we can guarantee that now the function is bounded from above and below. Now note in this approach, everything here is purely like algebraic and it's agnostic of your dimensionality element type. So the beauty is this approach works for different bases. The example used Gauss-Lobato basis, but you could use Gauss-Legendre, Bernstein bases. These bases have different applications. Folks use different bases for different fields. Works for different element types, different dimensions. So, the method generalizes. And if you're using our favorite tensor product elements, you can use the tensor product property to lower the cost. I just realized I skipped past the cost on the previous slide, so I'll go back really quick. The cost of this procedure is O of n times m. N is the number of basis functions. M is the number of control points you're using to build the basis. Okay, so back to tensor product elements. We can reduce the cost by using the tensor product property. So if you have a 2D function, you first bound the inner summation, right? That'll give you the bounds on the coefficient for the outer summation, and then repeat the procedure. And as a result, if now n and m are your 1D parameters, the cost ends up being n to the d times m plus n times m to the d. So in short, it's going to be n to the d plus 1. And, that's as cheap as it's going to get. Yeah, and so it's quite robust. You don't have to deal with like projecting to a different basis where you run into like conditioning issues if you're like projecting to Bernstein or whatever. Here, you don't need to change your basis. Okay, so now the question is, how do we build the bounds for our basis, right? There's a simple numerical recipe that's coming from GSLib, and what we do is take, we pick one of the basis functions, right? In this case, I have its cubic function on 4 Gauss-Lobato nodes, right? I'm gonna pick a set of control points to build the bounds. In this case, we choose 8 Chebyshev points. Okay, that's what the default choice is. And then for each of the control points, I'm gonna evaluate my basis function. Okay, and then I'm gonna evaluate or compute the tangents coming from the left and right midpoint between the control points, right? So you can't see my cursor here, but basically, so for this point, I've built the tangent at the midpoint between these two and these two, right? So this gives you essentially these three values at your control point of interest. And now your upper bound is just the maximum of these three values. Lower bound is the minimum. You repeat this procedure for all the control points, and you get the bounds for your basis function. So this is a simple numerical recipe, takes a few dozen lines of code. You can have it running fairly quickly. But a drawback is, so in this case, it works really well if I'm using 8 Chebyshev points. If you use fewer points, for example, 5, you see that it doesn't work. In this case, towards the end, you see the lower bound is intersecting your function, okay? So there's essentially a constraint on the number of points you need to use to get the bounding property. This is the table that shows how many Chebyshev points you need. Uh, so, you know, Zanio proposed, I don't know how he's like, I think Gauss-Lobato plus endpoints will do better. And it indeed does better. Somehow it like pick the best set, and you see you get you require much fewer points to get the bounding property. We also tried GLL. They end up being the worst, even though in this case your nodal basis is on GLL, right? Right. So this is one way to bound it, and then I talk about this in detail in our paper. That's what I presented last year. It's the general field evaluation in high order meshes on GPUs, right? Uh, a better way to do this is an optimization based approach, right? It'll work for, since we were trying to figure out what's the optimal set of control points, or like, why don't we solve an optimization problem? So in this case, the user just specifies the number of control points, and we figure out animation was supposed to play. Oh, okay, it's playing. So yeah, I show it for I think there's one animation for 6 control points. This is for 4. So as you can see, by solving an optimization problem, you can bound them for any number of points. And we talk about this in a recent paper. It's on arXiv. And note that this only needs to be done once for a given set of bases, right? So you could have 1,000,000 elements, 1,000,000,000 elements in your mesh, but you need to do it once. And then it can be reused for all the elements, because what's different is just the coefficients usually. Unless you have mixed meshes, then you can just do it for each element type. And in this optimization-based approach, you don't even need to solve that. We have done that independently. And we can make the bounding matrices available, so it just gets read in from a header file. Okay. Now, to increase the effectiveness, there's a couple of tricks. So I showed how we get the piecewise linear envelope for our function. One trick is you take your function, subtract a linear fit from it, and then bound that new function. So you see what happens if I subtract a linear fit and bound that. You get the bounds on that function and add back the linear fit, right? And now you see that the bounds that you get are much more compact, right? So that's one way to increase the effectiveness. Another is, as I said, it's up to you how many control points you use. So that gives you this user tunable compactness knob. You can use fewer points, but the bounds will be looser. As you increase the number of points, the bounds get tighter, okay? How does this translate to more practical things? So let's take a 1D example. Let's say you want to guarantee or determine if an element is valid or not. This is your polynomial. So that means you want to see if the minima is positive, right? And what I do is I use this way, I use this approach to bound my function, right? Now I inspect the values at each of the control points. Since now it's just a piecewise linear envelope, I check the value at each of the points, and I see at one of those points over there, it's the lower bound is negative, but the upper bound is positive. So that means in that region, I'm not really sure if it's completely positive or not, right? So then I can just refine my bounds or just bound that part of the function. And that gives me, tighter bounds in that area. And again, I see there's like one region where still the bounds have opposite signs, and I do another recursion. And by this point, I see that the upper bound has become negative. And when the upper bound is negative, at that point, I can guarantee that the element is inverted somewhere, right? Uh, that was just a 1D example. Coming back to our 2D example, I can do the same thing. I build my piecewise linear envelope, check the individual values, and we can see. So as I said, we can see there's like 3 local minimas. Turns out at 2 of these regions, the bounds have opposite sign. So I refine the bounds in that area, and then after maybe one more iteration, I get that the upper bound is negative, so I can guarantee that the element is valid. And comparing to what's currently used in the literature widely, with Bernstein, we saw earlier how the bounds converge, or how the minimum coefficient converges. And with our approach, you can, you see you get closer to the true minima a little faster, and I believe with less compute costs associated with it. Okay, but how do you use this in MFEM? Okay, so for an advanced user, you want to do funky things, recursions. One way is you build this piecewise linear bound object. You specify the number of mesh nodes, number of control points, what's your basis type, what kind of control points you want. The default is Gauss-Lobato plus endpoints. As I said, that's what we found to be more efficient. Or you can also use Chebyshev, keeping that for legacy reasons. But this is, I feel like, first of all, no one wants to use this, but this is for like more advanced cases. It's going to have its uses. So I think all of us would rather just use grid function get bounds, right? Because grid function already has all these things baked in. There's like a finite element collection with basis type associated. So we can pull all that information from there and get just global bounds on the entire function across the mesh, or get element-wise bounds. And the last 2 arguments in both these functions have some default values, so you don't even need to specify it. But if you want to like increase the compactness, you can increase the refinement factor, and the bounds will get tighter. So there's a couple many apps demonstrating this. I think Wesleyan hinted at it in his talk yesterday. There's one where you just give it a mesh. It's going to compute the bounds on each element's nodal position and give you the bounding boxes. It's going to compute the Jacobian polynomial, give the bounds on it, and then there's a general mini app to demonstrate bounds on any given grid function. Okay. Right, so that was the bounding part. I'm going to connect to it in my high order mesh optimization part of the talk. And in MFEM, we do mesh optimization with TMOP. And I was going to give you one slide on overview of TMOP, but there's paper for that. So I thought I'll like do an advertisement slide to show how our capabilities have evolved over the years. Okay, so this project started like back in 2016. And I'm going to use the years when we actually publish. It takes a time, especially for papers like in journals like CISC, the review process takes some time. So 2019 is where the first paper appeared. It's the paper that establishes TMOP for high order meshes. So you see a 4th order turbine blade and how we can optimize it for mesh quality. This was general mesh optimization based on elements agnostic of the solution. And naturally the next step was, how do you incorporate solution, right? So it's not very clear, but this is from a multi-material AL simulation. You have solution evolving in the upper half, and in the lower half we adapt the mesh. And it also leverages a new capability at that time called node limiting, where you want to optimize the mesh but don't want to change the resolution too much, because you might have constructed it carefully. So we tried to keep the nodes in their original position proximity, but still smooth it. In 2021, we did this thing called adaptive surface fitting, which is mesh generation via optimization. So you have a level set function. An isocontour of this function defines your target geometry, and we take a given mesh and adapt it to align with it, right? So this gives you a conforming mesh. Here you see an example of a chord mesh morphing to a circular interface and in 3D to a sphere. By the way, all of these capabilities are 3D. Okay, I showed 2D because they're easier to visualize, but all these capabilities that I'm talking about are 3D. 2022 extended age adaptivity. So you have your simulation. How do we also incorporate AMR to increase the the bang for our buck? How do we do we figure out where can we do age refinement combined with R refinement to reduce the error. 2023 we bring in GPUs, a lot of heavy lifting by John to extend it to GPUs. This capability from 2021 on surface fitting gets used for conformal shape optimization. So high impact application, you see in that case, the geometry is represented by a level set function, and we optimize it for stiffness. And at each iteration, we adapt the mesh to align with the actual geometry. So that's what you're seeing in the animation. In the same, same LDR, the node limiting capability also gets used for shape optimization. Yeah, and a shout out to Jorge Luis and Kenny Swartz who were involved in this LDRD. And then 2024, we did mesh RP adaptivity. Again, these are like really fundamental work. So here we morph or optimize a mesh, and we also do p-adaptivity, so you get high order elements only where it's needed. So in this case, you see a 2D version of the Apollo capsule. Elements are colored by polynomial order, so you get high order elements in regions of high curvature, low order elements everywhere else. And then a very practical development where we do mesh optimization with combination of different mesh quality metrics. And anyone who has done penalization based functions, it's hard to balance your different terms. So our customers wanted to like not have to tune different weights in our objective function. So this paper was about asymptotic analysis of these compound metrics. And that brings us to this year. Okay, now tying in with the bounding stuff. So one of the problems with this blade example, which most of you will not see, is when we optimize the mesh, we have always just guaranteed mesh validity at a set of quadrature points. And that's usually sufficient for 99% of the people because you just care about your mesh validity at the quadrature points you're solving the PDE with, right? But from our perspective, if we're going to give you a mesh, we don't want you to constrain what quadrature points you're using, right? So now we can use this bounding approach to make sure that the mesh that we return is valid. So in the mesh on the right now, I can use the bounding approach and guarantee that it's valid everywhere, right? So give it to you with confidence, and you can run it with whatever quadrature rule that you want. We also have mesh untangling. For mesh untangling, a common trick um, is to introduce a barrier in your objective function, right? So it's an optimization trick. You introduce a barrier to move your quantity of interest away from it. From untangling perspective, the barrier is based on the minimum determinant of the Jacobian. So until recently, we would do it by sampling the quadrature points and then offsetting that, but it's not very robust, not guaranteed to be actually below the minimum Jacobian. But obviously, what you can do is instead get a lower bound on your Jacobian now, and then we still keep the epsilon because if the turns out with our approach, if the minima is on the element boundary, our approach for bounding will catch it exactly. So just to make sure your denominator does not become 0, we still offset it. You can do 10 to the negative 10 if you want. And here, this is one of our benchmark cases from Pat's paper for mesh untangling. So you see a mesh untangled for p equals 1, 2, 3. More practical example of mesh untangling and a new capability. We have tangential relaxation on curved boundaries now. So until now, we would keep mesh nodes on curved boundaries fixed. We would only slide them on Cartesian aligned boundaries. But thanks to a capability we developed with Aditya Parekh, who was an intern here last summer, which is find points for surface meshes. We can now allow the mesh nodes on curved boundaries to move, but then do exact projection on the original surface so that you maintain your geometric integrity, and we don't introduce errors. So you'll see in an animation, the first snapshot shows the mesh untangling, and then we smooth it, right? And you see how maintain the geometry. And as I said, everything is 3D. Want to keep your confidence there. So here's a 3D example. In 3D, it gets a little more challenging because you want to make sure nodes that were originally on edges stay on edges, and nodes on surfaces stay on corresponding surfaces. So we do that. We're now extending it to interfaces as well, another layer of complication. So the first example is for exact interfaces. The second one is where you have volume fraction-based interface, where you might not have it exactly. That's very recent work that we're doing with Vladimir as of last week. Okay, the final new capability is PDE-constrained optimization, where you want to not just improve your mesh based on a snapshot of the solution or geometry, but you want to incorporate your actual PDE instead directly, so that the solution that you get is the best solution with that topology or resolution that you have. So it ends up being complicated because now you're solving a problem where your solution depends on the mesh nodes and you're moving the mesh nodes. So you get into the adjoint method. Won't go into too much detail. This paper is also an archive, should be published soon. But here we show an example of, for example, you're solving the Poisson problem. You can use different type of error estimators. So the first one is based on the solution average. All these estimators are essentially here to catch the gradients in the solution in some way. And you can see in all these different formulations, we can get the mesh to adapt around the region of interest, right? And they're all very practical error estimators. We're not assuming you have knowledge of exact solution. And we show at the bottom that you maintain the convergence rates. Again, works for all element types, 2D, 3D. So you see some example with simplices, hexes, tets. This is Poisson. We've also tried it for linear elasticity. The approach works as long as you have a well-defined adjoint operator, right? So in this case, we have a beam. I show the reference solution here. It's a cantilever beam being pushed down. And for quantifying the error, I measure the displacement at that bottom right corner. And this is the solution for the reference with a Cartesian aligned mesh. You see that displacement, it doesn't capture the reference solution very well, but with a little bit of optimization, we can do better. The exact solution is fourth order here, so that's why we can't get as close to there's only so much we can do here. And if we use a quadratic mesh, you see here, even though the initial mesh is quite close to reference, but you see on the right, there's still a difference. But with a little bit of optimization, we can just land right on what the reference solution is. Okay, really quick, last slide. Some other updates we have done with Matthias. We have introduced AD. So now we are able to tackle problems we couldn't do as robustly now. I remember Milan wanted to do some mesh alignment for tokamaks 3 years ago. We're struggling with finite differences, but you see, we can now do it, very robustly. And then we also have r-adaptivity for periodic meshes now. That's also of very practical interest. Okay, in the interest of time, is the summary, future work. And I'll open the floor to questions.
Really excellent talk. Thanks, Ketan. Got a couple of questions, but I'll try and keep it super brief. At the beginning with the bounding, two questions about that. I'll ask them at once so you can respond quickly. Do you have any theory for or reasoning behind why Gauss-Legendre plus endpoints is so good? And in that table, the number of control points needed to obtain accurate bounds, can you compute that number a priori, or is that based on just trying it and stopping when it works?
First one, I'm not sure that was Zanio's intuition. He could elaborate more on it. The second one, those bounds, those numbers, I have pre-computed for you, and I've put them so that you can't like use fewer points accidentally. So there are checks in MFEM which will prevent you from doing that. So that was just for your knowledge, but you don't need to worry about them.
But if I have my own basis with some number of basis functions, do you have a way of telling me how many control points I need?
No. Yeah,
So those
we'll have
numbers
to.
were just try those numbers and can I add something?
Sure.
So this is for this approach with the tangents. There's some interesting theorems to be proven there that have not been proven. But with the approach where you compute the best possible, the optimization one, those are pre-computed and those are verified, and the numbers, they are smaller.
Well, yeah, they even work for 2 points because we solve an optimization problem to ensure you're bounded.
When you do when you have positive and negative and you do the recursion, can you guarantee that the recursion terminates?
No. Yeah. Well, it depends. You can like eventually it will terminate, but you know the
Yes,
clause,
yes,
like,
you can. Ketan, you can. We have some theory that's not in the paper that will allow you, based on, for example, the distance from zero of the minimum, if the function is positive, what is the delta to the zero, to actually estimate how many times you need to refine. And it's a finite number, and you can actually estimate it in advance. That's the last thing we added, right?
Right.
That we will be at.
Enough questions.
I think we probably should move to the next talk. Oh, is there one to chat? When will this be used in GLVIS for adaptive visualization?
Oh, is that, who is that?
The chat.
Oh, that's a good question. It'd be nice to have this in GLVS to also get the bounds there.
All right, Milan has one last and.
Milan, XM Energy. Excellent talk. Very quick question. So you're saying you can find bounds of any grid function? I can imagine vector grid function as well. What about a combination of grid function, an ideal and nonlinear combination of grid functions? And I'm shooting for invariant domain preserving
Non-linear
information
combination of
extraction.
grid functions. Yeah, that sounds like an interesting problem. We haven't looked into it yet. Also interested in like, nerves type, like rational functions. Also need to look into that. Good question. Thanks.